Did you miss me? I miss me. Well, I mean, like this, I missed the series. What's up, guys? My name is Cherno. Welcome back to the ray tracing series. It's been a while since the last episode. I know, hoping to get back into it. Today, we're going to be talking about emission and emissive materials. And we're also going to take the opportunity to hopefully get in and clean some stuff up. So to put it simply, emissive materials are simply materials that emit light. Every other kind of material we've been working with, and I say material in quotes because our materials are really quite basic at the moment, but nevertheless, every material that we've talked about thus far absorbs light. What that means is that when we have a ray that comes in and it hits a surface such as this table, for example, that light that's coming in from that like window behind me, when it hits this table, the table absorbs some portion of that light and the rest of it is reflected somewhere. Now, we've touched on this loosely in the past, but the somewhere that it's reflected to will be determined by the actual kind of microfacet model of the surface. So rougher surfaces will scatter more rays kind of in different directions. Smoother surfaces will more or less just reflect it along the normal. Now, in an actual ray tracer, it's done typically in reverse. So the ray comes from the camera, which might be like our eye looking at this table. And what we're basically doing is reflecting this ray that's coming from the camera in some kind of direction. And then to kind of simulate the material absorbing some of that light, we have this multiplier variable, which we're halving every single bounce. That kind of simulates the absorption of that light, because eventually that ray will go out somewhere and it will hit the sky. Our scene is very simple. There's only two spheres, so it'll get there rather quickly. And that sky is kind of the light source that we have. But since the material absorbs some portion of the light, we kind of reduce the overall light power using that multiplier. Now, we also have this kind of directional light that we created. It's a little bit of a hack, but it's just a way to provide some kind of direct light to our pixels as well, essentially. So to summarize, what's happening is every time the ray hits an actual object, i.e. one of our spheres, it loses some energy. It doesn't gain energy. And in fact, every material that we have that is non-emissive in the real world will always absorb some portion of light energy. I'm not sure if it's like 100% physically impossible. It sounds like it probably should be, but at the very least, I can confidently say that it will never increase the light energy, again, unless it's an emissive material. In fact, that's one of the most important rules of a physically based renderer: energy conservation. You can't wind up with more energy after you hit a surface. The light energy will always kind of diminish. Obviously, it depends on the surface and even like the surface color. Black will absorb more than white. White will reflect more light. But even something like a perfectly shiny mirror, it does lose some kind of level of energy. That's why if you put like mirrors facing each other, so that you get that kind of like infinite mirror corridor, as you look into all of the mirrored reflections, you'll notice that they're getting darker and darker, because even though the mirrors are very, very reflective, they are still absorbing some light. Right, so materials and surfaces absorb some kind of light and reflect the remaining light energy, and that makes up our scene. But what if we had a material that actually did increase light energy? What if the material itself is kind of like emissive and glowing? That is essentially a material that acts as a light source. I think it's interesting that in kind of renderers, and not just ray tracers, but rasterized renderers as well, we have these kind of different light types. We might have a directional light, a point light, a spotlight, an area light, whatever. What's interesting is that none of these really exist, at least in that form, in the real world. Like, they're all completely fictional. A directional light, like what's a directional light? It's a light with no position, it's just a direction. That clearly cannot physically exist in the real world, but what it is a really good model to approximate how sunlight works and how the sun works, because the sun is this huge, powerful light source that's so far away that really doesn't have a position. As long as you're in one kind of position and don't go too far around the world, it's kind of like a light that covers an infinitely large area, and it only really has one direction. A point light is a light source that is infinitely small and just emits light in all directions. Like, that obviously cannot exist, because you can't have a light that physically has no volume or surface area. It's infinitely small, but it just creates light somehow. That's magic. That's fiction. Over here, I have a light. It has a filament, and that filament, when current flows through it, will actually create light. So let's think about this a little bit deeper. This filament is just a normal kind of material right now. It's just a material that absorbs light in this state. But if I turn this on, suddenly it's emitting light, right? So here it is, just absorbing light like any other material we've talked about thus far. And then suddenly it's able to actually emit light. Now, if you were in some kind of like game engine or maybe like a 3D program like Blender and you wanted to model this, you might just create a light. Like in our ray tracer at the moment, you'd be like, okay, well, I want this light source to be here. I'll just create like a point light or something. But my point really that I'm trying to drive home here is that this is kind of just an emissive material. So emissive materials are basically lights. And in fact, I'd go as far as to say that basically any light in the real world is just an emissive material. The reason why we have lights like point lights and directional lights is because it's a lot simpler to kind of model that version of reality, especially in rasterized graphics. But in a ray tracer, where we are physically just tracing rays and actually doing light calculations based on physics, essentially, this actually makes a lot more sense. And so what we're going to do today is jump into our code base, extend our materials to support emission, and then implement that into our renderer so that we can actually have materials that emit light. And in fact, we can turn everything else off, our stupid directional light that was just kind of there as a test, and then our skylight, we can turn all of that off and just rely on materials that emit light to light our scene. But first, before we jump in, I want to thank Brilliant.org for sponsoring this video. Brilliant.org is a fantastic sponsor for this series because they have, in my opinion, the best math courses on the internet. And math is vitally important for ray tracing. I would say like for programming in general, but like, I mean, if we take a look at some of the code that we're writing here, you know, like the sphere intersection, knowing things like the quadratic formula, solving these equations and like what to do with like the multiple solutions that you might get, that kind of stuff is really, really helpful. And I promise you that if you just take a moment to try and understand this stuff, you're going to have a lot more fun with the code you write because you'll be able to understand it on a deeper level and thus extend it and tweak it much more easily. The worst thing to do is just to try and like tweak the numbers until something magically works, and then it might not work in all cases because you have no idea what you're doing. If you're completely new to math, start with Brilliant's Everyday Math course. It's a really good, gentle introduction. If you want to get deeper into the kind of stuff we're doing here, Brilliant have everything from algebra to linear algebra to even calculus, which we'll touch on later. And the reason why I say Brilliant is one of my favorite places on the internet to do this kind of stuff is because all of their courses are really engaging. They have these widgets that you can play with to actually visualize how everything's working. That can be really, really helpful to help you understand. And then they'll also continually quiz you, which in my opinion is vital to ensuring that you actually retain the information that you're learning. And guess what? They have a 30-day free trial. Just go to brilliant.org/thecherno, link will be in the description below. Give it a go through some of these math courses and see if you like them. And if you do, Brilliant have been nice enough to offer the first 200 subscribers 20% off an annual membership. Huge thank you, as always, to brilliant.org for sponsoring this video. Okay, so the first thing that I want to do here is I basically want to go back into walnutapp.cpp and extend our kind of materials that we have here to actually support emission. Now, there's a few different ways that we can do this. The simplest way is probably just to create like a float called like emission or something. What I'm going to do though is create two variables. There's going to be an emission power, and then there's going to be a separate vec3 called emission color. And this can just be 0, like just black to begin with. But the reason why I'm doing this is because you can technically have a material that emits a different color to what it is, and this kind of model allows us to do that. And the reason why I've also split this up, because we could obviously, like this is a vec3, it doesn't have to be between 0 and 1 kind of for each component. It could be anything, is just to make the kind of IMGUI integration a little bit easier, because I want to treat this as like a color edit. So we have like a normal color panel that we can choose a color, but then this will kind of be a multiplier on top of that that will really just get multiplied. So basically what I'm saying is we'll multiply these two together when we do the actual calculation. And so because we're going to want to use it that way, I'm going to make a glmvec3 function here called get emission const, and it will just return emission color times emission power. Okay, so the next step is going to be back in Walnut app. We're going to expose this stuff into IMGUI just so that we can play with it. So we have over here all of our materials being drawn in terms of like our controls for IMGUI. So let's make a color edit here called emission color. We can get rid of the rest of this and make sure that we use the GLM value pointer over here. And then we'll have emission power, which will just be a float. I'm not gonna, so we'll make it from 0 to FLT max, which is just like the max floating point value. If you just set a minimum, IMGUI, at least this version of IMGUI, will not kind of, it won't do anything at all. So you have to kind of set both min and max if you actually wanted to enforce that kind of those bounds. And we of course don't want this to be negative. So 0 is the lowest, and 0.05 can be the kind of speed at which we change that if we actually drag. Okay, cool. So that looks pretty good. What we can do here if we want is we can set some initial emission, but I'm not going to worry about that for now. Let's add another sphere that is maybe, has a radius of 1, that's maybe like 2 along the x, and we'll give it a material index of 2. And so I'll just make another material here. Maybe we'll call it orange sphere. We'll set the albedo to be quite warm, maybe like 0.8, 0.5, 0.2, something like that. Hopefully that'll be a nice orange. Roughness, I'll just leave it that. And so what we're going to do with this guy, which, yes, I need to rename to orange sphere, is we will actually set an emission color. I'll just set it to be the albedo to begin with, and then emission power I can set to like 2 or something for now. Again, we should be able to just change all of this inside IMGUI, like inside our actual interface, so it's not going to matter too much. Okay, so let's hit F5. We're going to see, obviously, hopefully an orange sphere, but with no emission because we don't have emission. All right, and there we go. That is looking quite bright, but that's okay for now. Let's go in and first of all, just remove the directional light that we have. So if I go to the renderer, over here inside our per pixel function, which of course is like the main function where we do everything, these are kind of our light calculations. So we have this kind of light direction, light intensity. I'm just going to get rid of this. And then obviously sphere color times equals light intensity we can get rid of. And since sphere color is only used here, I can just use material albedo directly just to make the code a little bit more simple. So we're actually removing code. We're making this more simple. Let's hit F5 and just see the effect without any kind of directional light. Okay, cool. Looks kind of cool, looks very bright. In fact, looks kind of like we barely have any diffuse light. So let's go in and maybe change our model a little bit, because what we're doing here is kind of like a weird hybrid between diffuse and specular light transport, and I don't like it. So what I'm going to do is actually, if we go into random, inside this is walnut random, we have this in unit sphere function, which really all it does is it generates a vec3 in kind of like a -1 to 1 range, right? Across obviously 3 axes, so X, Y, and Z, and then it normalizes it, which will kind of make the length, 0.7, I guess, of each component. And we wind up with basically a vector that is in 3D space somewhere inside a unit sphere. This is actually a really handy function. It's not a great implementation because this will use the random number generator. It's going to be a little bit slower than something we'll switch to in the future, which will actually be something that we can use inside our Vulkan ray tracing shaders when we get there. That's going to be like, I don't know, at least 5 times faster probably than what we're doing here. And the other problem is it's in a unit sphere, which isn't a great kind of domain, I guess, that we want our random numbers to be in. Because what's happening at the moment is if a ray hits this, what we're doing is we're reflecting it just by the normal, and then the blue is kind of the output ray. We're also kind of jittering it based on the roughness of the surface, and that's kind of creating this. That's not how diffuse light works. This is mostly used for specular, and obviously you'll have like the microfacet model, and really this is like the BRDF, which is the bidirectional reflectance distribution function. But basically what I'm saying is for a diffuse lighting calculation, obviously like what we're trying to do is instead of sending rays from the light, we're sending rays from the camera. So if we do in fact hit this, we have to account for the possibility that actually in orange, light might come from here. Light might come from all directions. It really will come from all directions. The only directions that it can't come in, really, is from underneath, because this is kind of like an opaque, I guess, surface, and that doesn't make any sense. If you go into like subsurface scattering and BSS DFs, that's a different story, but for our kind of scenario, that can't be possible. So what we kind of like to do is look at a hemisphere and just be like, okay, well, for each path that we trace, let's send a random ray somewhere within this hemisphere. What I'm doing, and what I'm going to propose we do right now, is we're just going to use this in-unit sphere function, which technically includes all of this stuff, but it's not really technically going to create a worse image or an inaccurate image. It's just going to send out more rays that aren't as important, that will kind of not contribute anything, and it will make our rendering take longer. But in the future, when we look at importance sampling and stuff, we'll revamp this whole thing. Anyway, this is just so complicated, isn't it? I'm trying to not complicate it for myself. Maybe I should explain less. So in-unit sphere is what we can use, basically, is what I'm saying. So let's take this. So we currently have just GLM reflect ray direction, which is our incoming direction along that world normal, as I mentioned. And then we jitter it, and then we get kind of this output ray. But instead, what we could do is when we hit something, so I'll just comment this out so we can see what it was before, we can just set this kind of new direction, our new diffuse direction, to be walnut random in unit sphere. So this will just pick a new random direction for us to go in. Sounds kind of stupid, but let's take a look at the result. Okay, so this is the result. We're seeing like a bunch of light obviously reflected from everywhere. It is kind of overall bright. To make this a little bit better, what we can actually do is bias it to be in the direction of the world normal. So if we take this random vector that's in the unit sphere, but then we add the world normal to it, right? So we have the normal added to it, and then obviously we take the whole thing and normalize it. We're kind of pushing it to be in the direction of the world normal, but it still has some variance to it. So to do that, we can normalize payload.world normal plus this kind of random in unit sphere jitter, if you will. And you can see what that's done. It's made it ever so subtly different in terms of this kind of pink, I guess, being reflected off of this blue sphere. Now, there's still way too much light energy though, so let's fix that. At the moment, we have these two things up here and they're very important. We have a color and we have a multiplier. If we look at what this does, color, we're adding kind of albedo to it, which is already a little bit wrong because we can't add anything to it. The reason why we were doing this is because this kind of had to do with the directional light that we had coming in. Directional light's obviously add light. So this kind of makes sense. What I'm going to do, just for clarity, is I'm actually going to change these variables a little bit. I'm going to rename this color to be light. So now it kind of makes sense. Like when you see light plus equals this, it tells you that you're actually adding light power. And that immediately, hopefully, like kind of looks wrong, right? This kind of makes sense. Like we're adding sky color because the sky is kind of supposed to be a light, but this looks wrong. So that's good. Multiplier. Okay, a few things here. First of all, this is just a float at the moment. What it really should be is a vec3. Why? Because not to get too deep into this, but obviously, like we have a spectrum of colors. We have this kind of wavelength of light energy. When light hits something, materials will actually absorb certain wavelengths of light. So if we look at my water bottle here, this orange, right? Why is this orange? It's because when the light hits it, it absorbs pretty much all of the blue light, and it only reflects light that is kind of red and green. Of course, it reflects a little bit of blue light, but predominantly it's this color because when the light hits it, this material is capable of absorbing certain wavelengths of light and reflecting other wavelengths so that we can actually see them. So in a similar way, it doesn't make sense for our multiplier to just be a float. So I'm going to make it a vec3. We're going to initialize it here to 1, same as it was when it was a float. And this multiplier, there's a few different names that we could use for it. It could be like the color of our ray in a way, because as the ray bounces around and materials absorb certain colors, we're left with whatever like the remaining light energy in that ray is. I'm going to rename it to something called contribution. And that's basically going to be like the amount of color contribution that our ray carries. So at the moment we're halving it, but let's change the way that this is actually calculated. And it's going to be really simple, but the effect is going to be so dramatic. We're simply going to stop increasing light and instead change our contribution to be multiplied by material.albedo. So what are we doing here? Well, remember, this is starting at 1. So if we have something that's red, what's the albedo going to be? 1, 0, 0. So if we multiply contribution with this, what's happening is that these channels are basically being canceled out. They're being absorbed. And then this kind of channel or color wavelength is reflecting 100% of it. So therefore, we will see red light. Now notice this is times equals, and as long as this stuff is in between 0 and 1 and this starts at 1, we will always diminish. We will always either diminish or remain exactly the same as in this case. If we even had something slightly less red, it would actually absorb, which means we would progressively get darker. That's good. We shouldn't be able to add light unless it's a light source or an emissive material. So by doing this with our little contribution, and then remember, so we're not adding light anyway, we're returning light at the end here, but we're just kind of multiplying with the albedo to get the contribution. The only place where we add the light is over here, and we do sky color times contribution. Let's see what that looks like. All right, check it out. Doesn't that look cool? This looks so dramatically different. And this is diffuse only, so no reflections, no specular. We'll get to that later. But what we're seeing here, I think is pretty cool. I mean, if we zoom in a little bit, you can see the pink kind of reflected here. You can see obviously the influence of this blue thing up here. You can see the shadow that's being created here, this kind of natural ambient occlusion. And it really is ambient occlusion here because this skylight is kind of like an ambient light source. It doesn't have a direction or anything like that. Now, I also noticed here that for some reason the emission color is correct, but the emission power is 0. So I must have made a little typo. Yeah, okay, emission power, I used metallic. So this should be emission power. Let's quickly fix that up. And so now what I would like to do is I'd like to actually get this kind of emission power and this sphere that's supposed to be emissive to actually emit light. How do we do that? That sounds pretty complicated, doesn't it? No, not at all. Because guess what we have to do? All we have to do is take this light, and it doesn't matter, by the way, if we do it first or second, because they're not really going to be exclusive to each other, but all we have to do is take this light and just add the emission from it. So we're generating light, basically. And again, this light isn't really going to do much at this stage. You could multiply this, by the way, with material albedo so that you could still kind of absorb some of that, but we won't do that for now. For non-emissive materials, this will just add 0, so it won't do anything. But if something is emitting light, we're actually kind of creating more light. And so obviously that ray that contributes to a final pixel will have a brighter pixel. And everything along its path will also contribute to that. So let's hit F5 and take a look at that. We now have basically a light source over here. Now, if you were expecting to see like, you know, a glowing sphere like bloom, that's not going to happen here because that kind of glow, that's a post-process effect. Just like it is in a rasterized renderer, we would need to basically implement bloom the same way because it's kind of like a camera effect. So this actually is correct. Now, to make this effect a bit more dramatic, let's just get rid of our skylight. So what I'm going to do is just get rid of this, comment it out. So now the only place where we're actually able to gather light, because light source is 0, the only place where we're able to gather light is if we have an emissive material. So without that, our scene would just be black. But since we have an emissive material, check that out. How cool is that? Let's play around with this scene a little bit. What I'm going to do is just grab this sphere, which is, I think, this one up here. I'm going to turn off accumulate just so that we can play with these controls because I don't have them resetting everything. Let's move it like, I don't know, back kind of over here. I'm going to make it way bigger so that it's kind of like a sun. Continue moving it like back here, maybe make it even bigger. And then let's hit accumulate now. We can also play with the emission power if we want. So 2, let's make it like 20, reset, and take a look at that. Isn't that beautiful? I just think that looks really, really cool. Let's maybe fly over a little bit to here. And if we kind of just give it some time to accumulate as well, I'm going to leave this running for like 2 minutes or so, and we'll see what it looks like. Okay, so this is about 2 minutes in. You can see it's definitely much less noisy. You can also see the kind of light energy here reflecting onto the ground from this sphere, which is pretty cool. And look at this absolutely beautiful soft shadow. Like, just try and achieve that in a rasterized renderer, am I right? It's so difficult. But it just happens naturally, and that's one of the beautiful things about ray tracing. Like, did we have to implement shadows? Like, no, we don't. Obviously for like directional light sources and when we have basically things that aren't emissive, if we're trying to model those traditional light sources, we will have to do some kind of ray trace shadows and maybe some other algorithms. They're a lot more simple than like shadow maps and actually getting shadow maps to look good in a rasterized pipeline. However, you can see that we just get these kind of amazing looking shadows just for free. And that's just the beauty of ray tracing. And what you could do, absolutely, is you could just make an entire scene with this. Like, as I mentioned, emissive materials, that's basically how lights work in the real world. So there's no reason why you even need lights, really. Like, you could get away with quite a lot by just using this. Now, the biggest thing this is missing at the moment is the whole specular component. And obviously, like, the way that we're doing this kind of diffuse rendering is also not really 100% correct. And it will change depending on whether or not our material is metallic. So there's still a ways to go in terms of physically based rendering. But honestly, I just think this is just beautifully simple. Like, I mean, if we look at the code that we have here, like, I mean, this is our per pixel function. It's like, it's literally this. This is basically our entire ray tracer, excluding like the sphere intersection. And you can see just how cool it is. I mean, of course we could get rid of this. And then this is just what we're dealing with. Like, it's just amazing. It's amazing that that is really all it takes to make something as cool as that. So I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. I hope you're excited the ray tracing series is back. If you are, definitely show your support in the comments below. Don't forget to check out brilliant.org/Cherno. Link will be in the description below, and I will see you guys next time. Goodbye.